That's a great idea, Mark. I wanted to back up a little bit to going along with Mark's kind of like big picture questions here of scaling robot learning. And another one to go back to Mark, from your talk was sort of this question of scaling to what? You know, like, are we scaling to scale? And is scaling the end, or is scaling the means to an end? And sort of what does that end look like? A specific question I wanted to start off with, and this was a requested question from the audience I think is very interesting and relates to a bunch of the talks that we've seen from this morning, and these ones as well, is what might a robot foundation model look like? So, you know, to connect with, for those of you that may know, especially in the fields of language and computer vision, it's just kind of, you know, of course, it's been a gradual sort of thing, but in some ways, there's kind of been this step into this new era where a lot of research can be done just by downloading something that was pre-trained on a ton of data, and then you either zero shot or fine tune it for some new task. I think it's safe to say we don't have that yet for robotics. And a question is, what might that look like? How do we get it? How do we use it? How would it be tied to one specific embodiment, or would it work across any embodiment? I think it's a big picture question for the field. I don't know if the panelists have any thoughts.
Yeah, that's a really good question. So we have debated this a little bit amongst ourselves at FAIR already. What might this foundation model look like? And so far, the ideas center on the question, well, is there like this one representation for robotics, or should we think more about like these different components that we want to learn, right? Like all these natural language processing and visual representations, they might be useful for robotics. They might be part of the foundation model of robotics. And then there are the models of the robot interacting with the world that the robot wants to learn. That might be part of the foundation model. That's how far I've gotten with this in my mind, but I don't know. I'm curious to hear what you think, Mark.
Yeah, Mark, is the foundation model logic geometric programming itself?
Yeah, I don't know. So I also don't have a really good idea, actually. So sometimes I'm wondering, but really don't know, whether like in language processing and also computer vision, the tasks are pretty clearly defined, and people, the whole community very often is also happy with the task. They stick with the task, there's benchmarks on the task, and then they kind of have these foundation models that relate directly to these tasks. Whereas in robotics, I feel that it's not like that, and I don't really know why or understand why. And so, I mean, this morning we had this talk, R3M, it was, I think, which was cool and bold, and I like that. But I'm also wondering, like, the idea here was that we have a general purpose representation, and on top of that, what do we do? Like the kind of standard things like reinforcement learning and so forth. And so I'm not sure if this is, how do I put this? If this is like really the thing, the architecture or the system kind of view that eventually we will have, like in 10 or I don't know, 30 years or so about robotics, that the only thing, the only necessity is to have a representation and then do general purpose reinforcement learning. Maybe it's not like that, and we would need some much more complicated system assumptions.
Yeah, it's certainly tricky. I think the R3M paper is also very nice. That it has kind of somewhat of this feel of trying to have some type of general representation, but then it's very much on the vision side, doesn't directly solve the how to do action side, Mark, as you're pointing out. And maybe all we know how to do now is just use that with RL to figure out the actions. But then, yeah, that's certainly tricky. Another question.
Yeah, I was just gonna say that I guess if we're looking specifically for foundation models on the action side, then we probably want to think about the action spaces first, right? What are the right action spaces to consider learning the representations for, such that we can actually download this model if that's our goal. And then, of course, end effector control or end effector is a good action space, like the moving the end effectors of your robot. Yeah,
definitely. I think, as many of you know, in practice, like choosing a little bit of a designed action space for your sort of learning level of your robot can give you a lot of sample efficiency, that could maybe be very helpful. Maybe the sort of lowest level action space, of course, is just the raw joints of every actuator. That can be tricky. And then the big question for me is, is it only tied to one specific embodiment, or, what if I add a third arm to my robot, can I still use the foundation model? Or even if I just make one of the joints or one of the links longer, I think the embodiment conditioning is very tricky for sort of actionable foundation model in robotics. We can definitely take questions from the audience. So yeah, do you want to go in the back first, maybe?
Great. So I want to continue the thread on difficult tasks and generating difficult tasks for robots. And I'm basically wondering, do we even have the language to quantify why a task is more difficult than other tasks? What complexity? It cannot just be the amount of computation required, because have a robot go straight, the task can be go straight for 1 kilometer. And that's not necessarily a more challenging task than here. So what's the right way to describe complexity of tasks?
Yeah, so I totally don't have an answer. Also, no publications or anything on that, right? But I think being innovative exactly about that would be super good research. But I think it's not so far-fetched, because like Pareto optimality is a typical example, like diversity is an example, like the whole ideas of adversarial training are an example how you can kind of bootstrap actually the task. Adversarial training would be an example. You have two populations of things, the ones that create the task, the other ones that kind of solve them. And they always, play games adversarially. I'm not saying that any of this, is the right approach, but I think there is ideas around, and I think it would be interesting.
I want to do it. Another question, going back to some of the themes from earlier. Mark asked scaling to what? I want to ask this question again, and I want to try and see if we can come at somewhat of an answer. And I think, I think a lot of people here might be interested in scaling robot learning in general, and maybe have a variety of applications in mind, like medical robotics, warehouse robotics, whatever it is. I think for at least some non-zero chunk of roboticists, the sort of like goal of like a generalist robot is sort of very present. Again, maybe not for all, but for a good chunk of roboticists. And even in the description of this workshop, it was discussed like scaling to general purpose robotics. And I want to ask the question, what do we think is a useful definition of a general purpose robot? And at least one sort of comparison point that I want to point out is that a general purpose computer exists. Like, this is a general purpose computer. We all have general purpose computers in our pocket. And at least over in the definition in that space, a general purpose computer does not mean that it can compute anything immediately right now, but rather that the sort of hardware and low-level software infrastructure is there sufficiently such that knowledgeable people can program kind of any, we essentially have, Turing computers, although we're just, bounded by memory in certain ways. So there are, of course, and then there's also, of course, fundamental just computable constraints, we can't, solve NP-hard problems, et cetera. So I thought it was a helpful comparison point. Back to general purpose robot, or some other notion of sort of like an amount of scaling robot learning that we're maybe shooting for. What do we think?
So I'm kind of okay with the definition that the robot is capable to bring the physical state in any desired other state. That is possible, right? So just to have this general capability of physical manipulation to bring it in other states. And that means that it's not so much about semantics, but this is biased, for my research. It's not so much about semantics or so, or language interaction or something like that, but more general purpose physical manipulation skills. So I'd be okay with it. You asked the question earlier, like a foundation model or so, whether it would be bound to one robot or any robot. Mm-hmm. To me, that system would have to be capable to do that for any kind of embodiment. So that's, to me, what this general purpose reasoning would mean.
Yeah, I tend to approach this also more from the algorithmic side, thinking about it. So let's assume we have some hardware that can do most things that we care about. Then I do what I envision for a general purpose robot is that anyone, any user at home, non-expert, can teach whatever skill they want the robot to perform, right? Without having expertise of like tuning specific things, or I don't know, even having to do heavy programming. So that's kind of my vision of a general purpose robot.
Nice. Another question, to sort of think back a little bit and kind of, past handful of years, panelists have been doing research in this area for at least a handful of years. And I think it's been a very interesting time probably in the past, I don't know, choose N years in robot learning research. And if we think about the sort of what we might think is the path towards these sort of general purpose robots, is there anything about your perspective in the past N years, and you can choose N, 1, 2, 5, 10, whatever you'd like, that has maybe changed, like something that 5 years ago you thought this was the path, and now you think, nah, I don't think that's the path anymore? Or has it been logic geometric programming the whole way, Mark? Or what is that? What do we think is certainly a strong model-based assumption could be a strong path? What do we think?
I think it depends on what we all have, like different axes that we sort of combine in our research, right? And one of my primary axes has always been lifelong learning. That hasn't changed. I think we still need this. But then what we learn, how we learn, that might have changed. Deep learning obviously has become huge. And so this is something I didn't do much during my PhD, but I'm doing a lot now. But I still think about it from the lifelong learning perspective. So, yeah.
At least I can say that my views have changed a lot, like in the last, I don't know, 20 years or so. I mean, earlier work of mine was also completely about, probabilistic inference for planning, general purpose markov decision processes, and inference control and stuff like that. So very generic MDP kind of, or control kind of work, which I thought this is exactly the way to go. But then at some point I thought, actually I don't really understand how to bring these things to generate really complex like stuff in the environment. And so actually the logic geometric programming came up exactly because I kind of felt that these general purpose methods that I was working on don't really do cool stuff in the world. And so I was just asking myself that what would do cool stuff in the world? And then I ended up doing LGP, which is, I don't know, maybe hacking a lot of stuff or so, right? But at least I learned something, I guess. And so I think that's one maybe insight. I don't know if it's an insight that if you work too much on these general purpose things, that I feel that you never, I don't know, get a feeling how to create really complex stuff in the environment. And another like topic related to that is this of hierarchies. Somebody mentioned also hierarchies. So I've been thinking about hierarchies quite a bit, like in my career, also earlier about hierarchical reinforcement learning, hierarchical POMDPs and solvers for these general purpose, right? But somehow I felt we have these methods and write them down, but somehow they don't bring it in robotics. And so now that changed also for me. I think this general purpose idea of what are options or things like that, maybe these ideas of what are macro actions or options is not really the things that yield good hierarchical behavior in the real world. And LGP and these things are an attempt of mine to really touch the real world and think how the structures in the real world really would look like.
Yeah, Mark, as you know, but the video that you showed of like grabbing the red blocks, or especially the pushing one, of course, because pushing is so hard. I think that's for those of you that have worked on, if you try to imagine just doing imitation learning, even just to push the red block to the green block, as many as you might know, especially with this sort of full 6-off motion and being able to do it in real time, super robustly. That is very hard to do, I think, with a pure learning-based method. Mark, I have one specific question for you on that demo, actually, which is the cost function, sort of like, the idea of putting red or pushing red to green or whichever it was. what do you think is the most scalable way in your mind to sort of encode cost functions? Or which is another way of kind of, that's one approach to kind of get at the question of task specification, which, as many of you may know, I think task specification is actually, I wish we could make it sound more interesting. It just sounds boring, I think, task specification, but it's such a critical question, I think.
How you call it reward learning.
Reward learning, there we go. Thank you, Franziska. I think reward learning is maybe one approach to task specification. You could think of other ones too. Maybe it's the best. I don't know, maybe there's others. But yeah, Mark, what do you think about your favorite approach to do task specification?
So also really good question. And it's also somebody earlier also asked about this task evolution or like evolving tasks, and that bears exactly the same question, right? How do you even specify a task? So again, I don't really have an answer. I think if we are talking about a real 3D physical world, gaining manipulability, is that a word? Like gaining control over an object by touching it, by grasping it also, is a quite really general concept of a goal of, yeah, something you could achieve. And that very, very often entails many other kind of manipulations that you would need for that. So I think if we are really talking more about the fundamental physical manipulation things, maybe tasks could be more about these fundamental things like getting into touch with something or getting control over something as well. And from that one could bootstrap maybe many more complicated tasks, specifications, something like that. But I don't really know.
Certainly tricky. I wanted to open back up to questions from the audience for the panelists, including you. You had one earlier. I didn't want to skip you.
Yeah, so this is more of a comment that I just wanted to get additional thoughts on from you guys. Something that I was thinking about, okay, well, back to the question of what sort of generalizable robot we want, what sort of things do we want it to do? Well, I guess our best reference would be what can a person do so far, right? And something that I was thinking about in terms of what specific embodiments should this sort of foundational model contain, right? If you give a person, say, an RC car, they'll be able to drive it very, very quickly because they already have these general understandings of how the world works. What happens if you crash into something, to avoid that, right? And so this does seem to mean that you use these foundational principles of, say, physics, of, say, knowing to preserve the RC car by not crashing into a wall by driving really quickly or whatever. And you're able to generalize that to whatever different embodiment you actually happen to take on, right? Be it an RC car, be it, say, a robot arm or something that you can teleoperate. But then how do we do this computation, right? Sort of returning to what Mark was saying during this presentation, where do we apply learning in this whole situation? Do we apply it to physics? Do we apply it to these actual cost functions of knowing to preserve yourself, or what? So to ultimately build some sort of system that you can just hand it like an RC car or whatever, and then it'll be able to instantly drive it. And then one step up from that, how do we get it to do what we want? Going to natural language processing, where we do have these foundational systems, sort of, you get to say oh, hey, write me a Shakespeare play. And then it does that conditioned on just you entering in that. How do you do all that with a robot, right? Do you do language? Do you do something else? So yeah, those were my thoughts, and I wanted to hear your guys' as well. I know this is a super general thing, but
I think there's a bunch of awesome comments in there. One to respond to, I think, is humans, to your point of we can just pick up joysticks for an RC car and figure it out. Maybe arguably, whatever a foundation model is for closing the loop from observations to actions and generalizing over embodiments, to your point, maybe we have that in there. Maybe we have the foundations of language. We haven't read all the internet like some of these other foundation models out there, but we have the foundations of language, we have the foundations of vision, but we can also quickly learn to play a video game or teleoperate, an RC car is a type of robot. I think it's a very interesting point. Yeah, other reactions from the panelists.
Yeah, so that was hard to digest, like all the questions. I mean, I think one thing you said about when how could the car like adapt if it's like broken or something, right? Maybe my first reaction to that would be that also in robotics we very often focus on the robot, which makes sense as a roboticist maybe, but actually I think an AI system should in principle, or maybe not even think of the robot or the own embodiment as something different than the rest of the world, because I'm just part of the rest of the world, right? And so that's the first comment. I think there should be no difference between whether the car itself is broken or whether it sees another car being broken or something, right? And so in that sense, it just has to have a concept of cars that they can be broken or not broken. And if they're broken, that then the kind of dynamics they have is different, and apply this either to itself or to others. So that was that question about the car.
That's a very interesting way of thinking about it. I've not considered that. I think it's very.
Yeah.
It's very philosophical, Mark. Like the whole world is just like all the same state, and we just have limited actuation capabilities.
Exactly, the world is the robot, but we just have so little motors. Yeah.
Really partially. Just really partially.
That's right.
Exactly.
That's right. Other questions from the audience? How about in the corner here?
Yeah, so this question is related to all of this, which is, I guess, kind of the question is in some of the ways we're talking about this, are we actually biting off more than we can chew? You brought up the point, Pete, you brought up the point of general purpose computers, right? But often when we talk about robots as general purpose, the thing it sounds like we're trying to solve is make a surrogate human that can do anything with very little human interaction. Deploy it in the world, it solves any task magically. General purpose computers don't do that. You do not set your computer in front of a problem you want it to solve and it just makes it go away most of the time. So do you think the right way to target this is to say, well, we're done when robots can do everything people can do? Or should we be thinking of it more like an itemized task? Like, are we biting off more than we can chew?
I'm trying to understand how these are, you know, the different sides of one coin, because to me they're not. But I think.
Elaborate on why they're not.
Yeah, so well, first of all, I think sometimes, yes, we are trying to bite off too much at the same time. So I agree with this. But so what was the second part you said? Sorry. So are we either biting off too much or
do we, is the problem not solvable in the same way as computers? Is a robot not really, like, do we not have general purpose robots they can
Yeah.
on their own?
Or to put it another way, is our problem AI hard? And like what we're actually going for is, you know, GAI, general purpose AI.
It sort of sounds like what we're solving is general purpose AI. If we can't solve that, we can't solve robots. Is that true?
Mark shakes his head.
Yeah.
what do you have again?
No, I actually, so general purpose AI would have to be able to behave optimally or towards optimally in any possible world. Like that could be the 11-dimensional universe and other universe with other physics and so forth. That's what general purpose AI is, right? And they enumerate all possible universes by complexity, let's say, and then that is the prior over which they search for policies. So I think that's exactly not what robotics is about, right? Robotics would be much more about our particular physical world.
And I think an easy problem because we only have to solve this one.
Actually
Only Earth.
question. No, but seriously, I think, yeah, that's also the question. And that's the scientific question also. How easy is it actually to turn I mean, when I say now our understanding of physics, like we're physicists or we have understanding of physics, how to turn that into the intuitive physics that other people talk about that would enable the system to do that general purpose manipulation capabilities. And I think that's a really fair scientific question, right? And it's not so much, it's not only about whether we're capable to actually do it and engineer it or so. It's really, I think, scientific question. And actually, I kind of think that would be possible to have like AI systems that have this general purpose physical reasoning capabilities. Just for, you know, normal physical like manipulation.
So that's targeting a specific thing, right? Like normal physical manipulation, which is sort of separate from like full planning, right? Like being able to predict manipulation isn't quite the same as knowing what you need to do. I mean, we saw tasks where like you could pick up an object, but knowing sort of which objects needed to be near each other for a task to be accomplishable was very hard in earlier talks. Like a 20% success rate on those overall tasks, which is like a mix of planning and understanding.
Yeah, it's also cutting away a lot of things. I mean, they wouldn't have to understand humans, which is super hard anyway, understanding humans. They wouldn't have to understand like animals or the living systems or things like that. We're just starting with physics itself. So I think it's a fair thing to start with, right? I mean, they don't have to perform chemistry research themselves, these systems. That would be then like really a universal system, but that's not what I was talking about.
So you're sort of talking about encoding what we already understand instead of having them all automatically sort of become scientists themselves.
So I think an interesting question, Mark, to consider would be, if Mark's sort of saying I kind of want to stop at general purpose physical manipulation capabilities. But I think at least an interesting potential question is, if we allow that type of a robot to be conditioned on language from humans, then arguably that if we also require that, then that would require kind of the superset of full language understanding and general manipulation abilities. Because I could pose a question like, go read Finnegan's Wake, and then if you think that, XYZ, then go do this task. And you know what I mean? It's tricky.
Was there a question?
So that wasn't a question. That was just a comment. I think we're going to close up here shortly, but we have time for one more question from the audience, if anybody has an additional one. How about back here in the corner?
Yeah, so I'm coming at this from a bit more like in the industry perspective, but to what level do we need generalization? I think the question is, like, if you look at like scaling across tasks versus scaling within a particular task, and you break down the different types of tasks, looking at the computer vision, result for instance segmentation, object detection, that kind of thing. We have a set of tasks that we can generalize within the process. That's the way that we should.
I'm not sure I understood the question, but I think you're asking, should we look at learning representations that generalize across tasks? Within tasks. Yeah. Yeah. Well, I like to think about it this way, that if we want to achieve sample efficient learning in the real world, we better learn representations that generalize as much across different tasks as possible, so that we can reuse knowledge from previous tasks that we've learned. I don't know how much we're doing this right now. I think some of us are. That's how I like to think about it.
I mean, you were asking, do we need generalization? That depends on what you want to solve. If I think about now industrial applications, so let's think about what could be industrial applications. You could think normal way and say the robot has to pick some stuff and do manipulation. You could also think that actually the AI system is supposed to reason about how to design a logistic facility building, right? I think that's, and then again, the building is the robot. With all the little robots inside. And I think in principle, whatever systems we work on, the research that we do should also eventually be able to address these kind of problems. But the same, you've seen this little architecture demonstration maybe that I had on one slide. Same thing here. You could think that the goal of robotics is to have one robot manipulating a piece, or you could think that the goal of the research is to have the AI system that plans and conceives of the full system and all the robots doing the things. Okay, and if you have this higher level like view of where this research should eventually end up with, then yes, you have to generalize across tasks.
Thank you, Mark. Let's thank the panelists for their time and talents, and also great talks from earlier.